right, it's absolutely wonderful to be back at Slack as always. Actually, thinking about this talk, I remember that almost exactly 10 years ago, a little bit over 10 years ago, I gave the first talk I ever gave on scattering amplitudes in this very room, with Len sitting there, and maybe not there. And already 10 years ago, I was making people suffer through the same words that I'm going to say again at the beginning of this talk. Okay, but I'm going to say them again anyway, and talk about some of the things that have happened in the intervening 10 years. So back then, at some point in the talk, like many other people, we can talk about this picture of a version of the idea of emergent space-time, at least for emergent space and anti-de Sitter space, where there is some boundary observable, just like we care about in scattering amplitudes if we happen to live in anti-de Sitter space, that we don't, but if we do, the boundary observables we care about are these things that live on the walls of the box in anti-de Sitter. And here, the basic ideology that you should try to learn how to calculate these observables at infinity by a theory that lives at infinity has been gloriously realized in the gravity duality. But one of the lessons from this picture is that there's a fundamentally quantum mechanical system that's king, and that space and gravity and strings and all sorts of other stuff emerge from the dynamics of that theory in a way that's still being more and more understood. But a very important thing is that it's not emergent space-time. The time that flows on the walls of the box is the same as the time that flows in the middle, and that's one of the reasons why this thing could be discovered by human beings and understood by human beings, because you don't have to change everything. You don't have to figure out, in particular, how to think about physics without time. And that's the main challenge, is we try to get closer to the real world. And there are two steps to get closer to the real world. Step one is what almost all of us in this audience spend a lot of time thinking about, the theory of the S matrix. The theory that the world is very close to flat space. And so here, there's an observable that also lives, in some sense, on the boundaries of Minkowski space. And of course, even closer to the real world is cosmology. The world isn't flat, so on really long distances, the world is cosmological. Here, the boundary observable is even more minimal than the S matrix. It's what's pretentiously called the wave function of the universe, and it's just a thing that calculates spatial correlations in the deep future. And in both of these cases, the observable that lives at infinity, unlike anti-de Sitter space, there's no useful or obvious notion of time or locality that lives on these boundaries. So, once you get into this headspace that you want to build a theory that lives on the boundary in anti-de Sitter space, you ask what the boundary looks like. It's a normal place. There's a notion of distance, time, locality, so it's reasonable for there to be a quantum field theory that lives there. But what about flat space, or even cosmology? We don't have any of those luxuries. And so the words that have been making people suffer listening to for 10 years is that we should be looking for something like this instead. It's more speculative, it's more radical. It's some other structure, some question mark structure, out of which we should see not just space, but space and time emerge. And there was already from very early on, there was circumstantial hints that whatever this picture is should have quantum mechanics come out together with space-time itself. Certainly, if you don't have a useful notion of time, there's nothing useful for a manifestly quantum mechanical description to do. And so this is a reasonable thing to expect from this admittedly vague speculative picture. All right, so let's get a little more concrete. What does this boundary of Minkowski space look like? We can talk about it geometrically. We can talk about it. In terms of whatever set of variables you want to use to talk about the on-shell kinematical data. But that's what it is. So the observables in anti-de Sitter are boundary correlation functions are labeled by points on the boundary of anti-de Sitter. The observables in flat space with scattering amplitudes are labeled by null momenta, or twistor variables, or momentum twistor variables, or variables on the celestial sphere. There's millions of ways of labeling what this data is. But whatever it is, this is some kinematical space. This is a space where amplitudes really live, where they're functions of these things. And as I said, there's no obvious notion of time or locality in this space. So just given this seemingly arid place, all you have is this data and nothing else, your task is to try to find a question, some ideas, some structures, something to do in this space that kind of breathe physics life into it. A question that you ask here, whose answer gives you scattering amplitudes with all the richness and complexity that we know they have. And the picture that's been emerging over the last 5-10 years or so And actually, until last year, until about a year ago, I couldn't say this. Even up to a year ago, all of these fancy things, positive geometries, canonical forms, all these things were living in auxiliary spaces, other places, Rachmanians, world sheets, other places. But starting about a year ago, we're starting to see all these structures show up where they belong in the kinematic space, in the space that actually labels directly the particle momentum. But in all these examples, there's something fundamentally combinatorial that's associated with something positive geometric, and there's a differential form, there's a kind of canonical form that allows you to extract physics from this geometry. So this is a general picture that we talked about amplitudes at Amplitudes last year. So in this kinematic space, there's a kind of a positive region that has some good positive properties in blue here. So you have this big capital D dimensional kinematical space. But the scattering amplitudes, or in cosmology, the wave function of the universe, is associated with some lower dimensional form that lives in this big D-dimensional kinematical space. This form is determined by a geometric condition. That there's a family of subspaces with the same dimensionality of the form, such that that family of subspaces intersects this positive region in a shape that's a positive geometry, and that this form is the canonical form for that positive geometry. So that's how life starts being breathed into the space, is that you find interesting combinatorial and geometric regions in kinematical space, and you ask appropriate questions of those regions, and those questions turn out to be local unitary scattering. All right, now just in the past year, we have sort of two examples of this, so it's a little bit strange that we have two rather different examples of this phenomenon. The basic structure is exactly the same, but the nature of the kinematic space and the positive regions are different, and the nature of the differential forms are different. So in the case of the amplituhedron, this is something, or this new picture of the amplituhedron in kinematic space, this is something that geometrizes helicity. So here we have scattering forms that are literally the scattering superamplitude for n equals 4 super angle, and you can do generalizations of this even for the standard model. But the idea is that the super variables are replaced with just differentials. And so when you combine the different helicities together with these differentials instead of with the super variables, you get a differential form. So that's the story for the amplituhedron. The story for the isopsahedron, bi-adjoint scalar theories, gluons, nonlinear sigma model, and so on, and any number of dimensions, there the forms are in Mandelstam space. They're differential forms in Mandelstam space. And somehow these things geometrize helicity, and these guys, their purpose in life appears to be to geometrize color. In other words, these objects have all the same properties as color factors that you would have going along with the diagrams with the same singularity structure. So here are some examples. In the case of the amplituhedron, we're normally used to seeing something like an R invariant. In this picture, instead of having an R invariant, there's a 4 form that goes with it. The etas are replaced with VZs. And once you write it in this way, it has some beef to it, because in this form you can recognize that this is actually the wedge of the d log of 4 things. And once you see it as the wedge of the d log of 4 things, this starts telling you a geometric story. This is the geometric story that's invisible in that picture. So you think of it as a differential form in kinematic space, and it begins to tell you a story in kinematic space. The same thing happens for scalar theories in a different way. Instead of writing 1 over s plus 1 over t for 4-point scattering like this, there's a differential form that goes along with it, which is d log of s over t. And here, these differential forms have some interesting properties that make facts about phi-cube theory that are otherwise hidden manifest. One of them is the remarkable fact that these differential forms are projective. That means they're not only defined on Mandelstam space, but the projectivized form of Mandelstam space, where you can rescale s and t, in this case, by any function of s and t. And that projectivity means that it's not a feature of any primary diagram individually, it's only a feature of the full sum of all of them. It's kind of a loose analog for phi-cube theory of dual conformal invariance for n equals 4 super angles amplitudes. And it's associated with different formulas for the scattering amplitudes that don't look like the sum over primary diagrams. And it's ultimately deeply related to color kinematics, as we talked about at Amplitude class. Okay, so here's now a kind of the emerging list of positive geometric objects and the corresponding physics that they have to do with. So for a long time, we were dealing with the amplituhedron in some Rachmanian space, And as of last year, we could start talking about it in momentum twistor space, as I will review. And that picture that we could see things in kinematic space is what opened up the road to see all these other things in a unified way. So, as we just said, we have a wide variety of theories here that are associated with the association and various cousins. And as I'll also talk about, finally, I've attempted to talk about the subject at a whole bunch of meetings and have never found the time to do it. So this time I'm punishing myself to find the time to talk about it, because there's some new work that we've been doing with Paulo Benincasa that very much relates to the scattering amplitudes in an interesting way. So there's even an excuse to do it, and hopefully I will get there. But anyway, for the wave function of the universe, for again a wide class of perturbative calculations of the wave function of the universe in polynomial interacting scalar theories, there are cosmological polytopes. And as we just heard about from Newton, there's now even in more far-flung things, the structure of effective field theory and conformal field theory, the same kind of ideas over and over again. Although here we don't yet have we don't have any analog of these canonical forms or anything like that. So here it's really just geometry at the moment. It's not as developed. I think it's not quite as interesting as these ideas yet, but we'll see where they go. All right, so here's the outline for the rest of the talk. I'm going to talk about 3 topics. First, I want to talk about the theory and practice of the amplituhedron in kinematic space. And I'll tell you how to think about the amplituhedron in the kinematic space, in the twistor space. I'll make a natural speculation. It's a pure speculation at the moment for something that might play a role for the actual amplitude, the integrated amplitude that the amplituhedron does for the integrand. Okay, so if it's possible to have an uglier word than amplituhedron, it's hard. Amplitude-dehedron is the best choice for the worst possible word. Okay? So, all right. Then I'll be brief about part 2 because Song is going to talk about various related things, but I'll talk about the 2 things that we won't have time to talk about. Going back to the story of the isosahedron, I want to sketch a new way of extracting amplitude from these canonical forms. Instead of this fancy business with pulling back and all this stuff, you just integrate them. But it turns out that to integrate them, you have to regulate them in a canonical way. And the act of that regularization leads you naturally to things that look like string amplitudes. Okay? So if you take the alpha prime goes to 0 limit of these objects purely as regularized things, they look like field theory amplitudes, but if you keep them at non-zero alpha prime, they look like string theory amplitudes. That's, I think, very interesting. And I will sketch for you an avatar of the worldsheet in kinematic space. So no a priori picture of a disk with the ordered points around it, but just a natural feature of the construction of the isosahedron that we found. This is not one of the standard ones that the mathematicians have talked about. It's closely connected to one of the ones Koslikov talked about, but it's not one of the standard ones. This picture of the isosahedron is very naturally comes along with a way of seeing an image of the worldsheet directly in kinematic space. And this picture for how you get numbers out of forms is naturally associated with these ideas. Isosahedra and string-like amplitudes from some notion of UV completion. Again, I'll be pretty brief with this one. And finally, I'll move on to cosmology. First, again, because of physics, the world is ultimately cosmological. And so we should ultimately be caring about the wave function of the universe. But more technically, the perturbative calculations of the wave function of the universe are a small generalization of the calculation of scattering amplitudes by precisely a single variable. So the wave function of the universe is a one-variable generalization of scattering amplitudes, which I think has lots of interesting and rich structure. And here I want to talk about in more detail the relationship between the scattering amplitude and the wave function of the universe, and talk about how the cosmological polytope, and a particular face of the cosmological polytope associated with the scattering amplitude, actually has Lorentz invariance, and the way in which the expected Lorentz invariance and unitarity of the amplitudes come out of this polytope. And it's very interesting, as you'll see, this polytope is somehow geometrized as a whole class of objects that you get from the Feynman tree theory. So it's very closely and interestingly connected to a scattering amplitudes in a novel way. All right, so topic 1 of the kinematic space amplituhedron. You've seen earlier today what the definition of the amplituhedron was, and in the standard way of thinking about things, we have some K plane that lives in K plus 4 dimensions with positive external data. and is defined by y equals c dot z, but that's not a useful way of checking whether a given y is in or out of the amplitude. So you might want to find a useful way of characterizing when y is in the amplitude. And this is what we did with Hugh Thomas and Yara a little over a year ago. So that's a question. When is y in the amplitude? And the answer to this question involves projecting through y down to a four-dimensional picture. For physics, for tree amplitude, we care about n equals 4. And now it's natural gas in the projected picture. Now the z's that you're left with in the projected picture are precisely the ordinary momentum twisters. And you can ask, what does that configuration of momentum twisters look like? For example, is it still positive in the sense that the underlying data was? And it is definitely not positive. Okay, so being in the amplitude puts some particular requirements on what the momentum twister picture looks like, and that's what we figured out with Hugh. Okay, okay, so this is what the picture is. Again, this is from a slide from Amplitudes last year. So back in this general picture, here we have the 4 times n dimensional kinematical space. Here we have a family of subspaces. But what is this positive space? There's a most primitive way of talking about what it is that involves projecting through the external data down to 1 dimension and simply counting a bunch of sign flip patterns. So something we call the amplitude's binary code, or it has maximal winding number. But you can forget about all of that, and and this implies the following most minimal description of what it is. Okay? So directly in momentum twister space, we have momentum twisters and we have the lines AB that give us loop momenta, and we just want the following region. The region where the obvious poles are positive, which is not enough, and you have to have certain pattern of minors have an appropriate number of sign flip patterns. So all of the factorization poles are positive, the poles with each loop momenta and the external data are positive, the loops are mutually positive, and these sequences have k sign flips and k plus 2 sign flips. This might seem a little bit funny and weird, how this I plus 1, jj plus 1, how the structure came out. There's something more primitive that just follows from this binary code, but you can read our paper to see what that more primitive thing is. But this is that's it. That defines the entire space. Okay, so that's this positive region. Now what is this affine subspace? It's nothing other than what you get by choosing some particular set of z data and translating in the direction of some particular k-plane in n dimensions. It's some affine subspace in a big space that's 4k dimensional, and the intersection of this guy with that guy in momentum twister space is the amplitude. But now in momentum twister space, there's none of this business anymore with all this funny, weird business that none of us liked, that the Z's had all these extra components, where the Susie went, and all that stuff. That's all gone. Things now live dead on in momentum twister space, but we have a differential form dead on in momentum twister space. That's the canonical form for the momentum twister space amplitude. And that's the superamplitude. You don't have to do anything to it. You just beat off the superamplitude. If you insist on making it look like a superamplitude people are used to, you take the dz and replace them with etas. Okay, so that's the thing. All right, now let me give you some quick examples for how you actually do computations with this picture. Okay, so let's calculate the one loop amplitudes. Okay, so one loop MXP amplitude is very simple. All we have lines AB in momentum twister space, and this series, AB12 up to AB1n, has to have k plus 2 equals 2 sign flips. So that means that this sequence somewhere it has to go from plus to minus and then minus back to plus. So the place where it goes from plus to minus, call that I. The place where it goes from minus back to plus, call it J. Clearly, these regions don't overlap with each other, and the union of all of them covers the entire space. And in each one of these regions, A and B, if we expand them on, as we are always free to, on simple planes like 1i plus 1, 1jj plus 1, there are 4 sets of positive expansion in this way that we've been familiar with for a long time. So this series of pieces triangulates the whole space, so we immediately get the canonical form, which is the usual Kermit formula that laws are used to for the MHD amplitude. Okay? So there's no recurrent relations, no BCFW, nothing. Okay? So it's just counting sign flip patterns, and looking at the sign flip patterns gives you the answer for MHD1 loop. All right, now that's very simple and familiar, but I now want to talk about some work in progress with Yara and a couple of our students, Cameron and Akshay, which was actually this was, I should say, that previous picture was impossible to work with, was impossible to say in our previous picture of the amplitude. It's something that we could say that now we can think about the amplitude in momentum twisters. And so we wanted to just keep going with this and see what else was obvious here. So something that we did a long time ago was use the amplitude to calculate lots of cuts of 4-point and higher point amplitudes. But this picture suggested a particularly interesting cut to talk about. We can call it the maximally intersected cut. This is a cut of the MHV integrand, or MHV bar, where all of the loops intersect each other. Okay, so all the intermediate loop lines are put on shell, but they don't necessarily intersect any of the external lines. So geometrically, we have a whole bunch of lines A, B, and they all pass through the same point A. If the full form is a 4 times L form, this is a 2L plus 3 form on this cut. So it's kind of halfway to the full integrand. Okay? So it has half the complexity of the full integrand. And I mean, I don't know what half complexity means. It's halfway to the full integrand. But interestingly, it receives contributions from all local integrals. It's not like other things we've done, like ladder cuts and other things like that clearly receive contributions from only a fraction of all the local integrals. This is deep inside, very complicated internal loop integrands will contribute to this cut. Now, what does the momentum twistor amplitude say? It says that the mutual positivity conditions have been trivialized. We just say that they're all positive. And therefore, all we're left with is saying that these AB alpha ij are positive. I should have told you that for MHV bar, it turns out that the sign flip pattern is exactly the same as this simpler state. That's something we also pointed out with Q. So all we have to do is demand that each loop momentum by itself satisfies this AB alpha ij as positive. Now, this is really interesting because just in the geometry, it appears that all we have to do is solve a one-loop problem. All we have to do is look and see what do the ABs look like in the one-loop amplitude. And after we solve that problem, we're done to all loop worlds. Okay? That seemed a little too good to be true, so of course we tried to do it and check that it's true. Of course, it's true, but you'll see that it's true in an interesting way. So what is the geometry problem? So here's what we're trying to do. And it's amusing that we were never forced to do this before, when we were thinking even about one-loop MHV amplitude, but it's a very natural geometric question. AB are lines in momentum twistor space. So you want to know what are these lines inside the amplitude geometry. But now we have a little bit more. We have this marked point on the line. So you can ask the following question. Pick any given point in the P3 of the momentum twistor space. Which lines through that point lie in the amplitude? So that's the geometry problem that we want to solve. Okay? And of course, depending on where this point is in P3, the region, depending on where the intersection point A is in P3, the line AB will lie in different shaped regions. Okay? So you want to kind of divide all of the momentum twistor space into the A's and then the associated regions in AB that goes along with them. And so this is purely a geometry problem, and we tried to solve this problem manually for n equals 4, 5, and 6, and then we saw a pattern. So we haven't proven that the pattern, we haven't yet proven directly from the geometry that the pattern extends to all n, but it looks very plausible that it does, so let me just assume that it does and tell you what it looks like. So here's what it looks like. When, this is all for MHV bar, remember. So when A is inside these tetrahedra bounded by these vertices, I bar, these are the usual bars that have to do with parity computation. When it's inside this tetrahedron, when A is inside this tetrahedron, AB, the corresponding B, is bounded by these lines. I minus 1, I plus 1, I plus 1, I plus 2. Okay, that's one case. When A is inside this dual of the cyclic polytope, bounded by these vertices, then AB is inside this triangle. It's now bounded by I minus 1, I plus 1, j plus 1. And the most generic situation is where this turns into a cube. Okay? So where there are 8 vertices of the form I bar, j bar, k bar, with those plus 1. There are 8 vertices here. And when A is inside there, AB is bounded by, oops, oh, I didn't change anything, sorry. This was supposed to be I plus 1, j plus 1, k plus I bar. All right, but that's what you get from the geometry problem. And then that gives you a formula for the form. Okay? infinite loop order and for any number of particles. And it actually collapses to this remarkably simple expression. So this part of the form is the A geometry part. And this product over alpha is the product over loops. This is the factorized A-B geometries. So the fact that it's factorizable in that form is the thing that's surprising, but it's not any standard recursion formula at all. But that's what we get. All of these poles are actually spurious. So when you sum over all of them, you get a manifestly local expression with only ABs downstairs, which looks horribly complicated. It was written in local form. But the Amplitude geometry gives you this beautiful one-line formula. And I believe this is the first non-trivial result in n equals 4. It's for a cut of the integrand, but it's valid for an infinite number of particles and an infinite number of loops. All right. And I should say this new kinematic space definition of the amplitude is absolutely critical to this. We had no idea even how to start doing this without this picture. Maybe someone else does, but we certainly didn't have any idea how to approach this. All right. Now let me just make another very quick statement. As I said, this is just a speculative quick conjecture at the moment. It's a very natural conjecture for what cousin of the amplituhedron should have to do with the amplitude. So the amplituhedron knows about the singularity structure of the integrand. And you might wonder, what should know about the singularity structure of the actual amplitude itself, where the branch points are, and so on. Now, we know from the beautiful work of Mark, Nassia, Vergu, Gantra, all these guys for many years, that somehow those branch points are associated with the cluster structure, at least for MHV amplitudes. And we've also known that that cluster stuff and the positive Rashomonian cluster stuff are very closely related to each other. But the relationship is actually really trivial. When you talk about the positive Rashomonian or the amplituhedron, the z's are not thought of projectively. They're really vectors in 4 dimensions. And that's very important because they carry the overall, the overall scale they have carries the helicity information. However, when you're talking about the polylogs, you're interested in cross ratios. So you really are interested not in the z's, but the z modulo little group. So there's a very simple question. Given, let's say, the positive Rashomonian, what is the positive Rashomonian modulo the actual little group? Those are 2 different spaces. And in the world of the positive Rashomonian, that's exactly the relationship between the A cluster picture of the positive Rashomonian and the X cluster picture of the positive Rashomonian. So, and given that we know the X cluster picture of the positive Rashomonian for MHV is so important for determining the possible symbol entries and other things, it's natural, now that we have a picture of the amplituhedron itself directly in momentum cluster space, it's natural to just extend that and see what it looks like. So what are we doing? Instead of just saying for general K, so this is really about just extending the picture that's been talked about before for general K, we're now interested in not just in these things being positive, but for general K, there's a region you can think of as something that's indexed by K for n equals 4 and n, where not only are the I plus 1 infinity plus 1's positive, but that the sequences that we talked about before have K signposts. The particular case of the positive Rashomonian is when K equals 0, so we can think more generally what this looks like. And so, again, in the usual story, and this is something we understand sharply, that the integrand form has d log singularities, and that's associated with the boundaries of this space. You might think the singularities of the amplitude itself, the branch points, would have something to do with the boundaries of this space mod little group. And as I said already, in the particular case of MHV, that's exactly what we've been told for many years. So I don't have much to say about this, other than the fact that Song and Mark and I have at least taken a look at what this space looks like for the first interesting case of NMHV 6 points. And if you're familiar with the cluster story for 6 point MHV, the boundary structure of this space is this beautiful associahedron. It looks like a simple polytope. And I really have 0 time to explain this, but we've at least worked out the boundary structure of this funny, flippy region is. And it doesn't look like one of the standard cluster algorithms people talk about. It looks like a torus, in fact. It's very interesting. And this torus touches the normal 6-point associahedron that we associate with MHD on 3 of these square faces. So it looks like, as Mark likes to point out repeatedly, it looks like bathroom tiles. Okay. We have this torus, and the torus touches the ordinary associated region on 3 of these faces. So how precisely this structure is related to the branch points of the amplitudes, there's even a question at tree level to think about the differential forms and see how the singularities of the tree amplitude are related to this. All of this is a work in progress. But I just wanted to say there is this natural thing to do. It may not end up meaning anything, but there's a totally obvious question to take, which we can now talk about, which we couldn't talk about before. We can now take the momentum twistor amplitude and just ask what it looks like after we mod up by a little group, and hope it has something to do with the branch cut structure. Yeah. All right, now let me move on to the second topic. Oh, and I'm super dead this time. So, okay, so let me say this. All right, so let's begin here with something Son will talk about a little bit more amongst other things that he's going to talk about. But we've had this idea of canonical forms, and we wanted of the amplitude associated with forms, and we want to extract the actual numbers out of them. Okay, so the usual way we've been doing this is by pulling things back to subspaces and stripping off various factors in a totally well-defined way. But there's a more obvious way to get a number out of a form. You just integrate it. Okay, so you have a canonical form associated with a region, once it looks like this pentagon. You can integrate it. Now, just for units, for it to have the same units as before, you have to put something with some appropriate units of mass squared here, so some alpha prime to the d, for this whole thing to be well-defined. But there's a bigger problem. This thing has logarithmic singularities on the boundary, so this integral diverges. That's why you don't do it. But there's a completely standard way of dealing with this that goes back to ancient times in the math literature, which is it's diverging because the form of logarithmic singularities on the boundary. So just add factors, powers, that damp the contribution as you get close to the boundaries. So now what we're going to do is associate with each one of the faces of this guy some variable little f, and just put some damping factors. So this is a canonical way of regulating these forms. And it's a regulator. At the moment, it's just a regulator. So if you take alpha prime goes back to 0, we just get back, in this case, just a function, which is just 1 over the sum of all the fi plus 1. So you have a canonical form, but you can also just get a canonical function out of this. And the function is a function of variables that you associate with the faces of the polygon. Now, as I've described it, it's clear that this function only depends on the shape of the polygon, but not anything about its detailed structure. So for instance, if I take this fat pentagon and this very skinny pentagon, I'm going to get exactly the same answer. But it's natural to ask, what would happen if you went all the way and you degenerated this to a triangle? And if you degenerate it to a triangle, you won't get the same answer. In order to get the same answer, you have to add some extra factors, some extra walls, some extra factors that diverge near these corners, and you can predict exactly what those factors are by what you have to match up here. If you're going to degenerate this to a triangle, you have to add these extra factors that go like the face that you were blowing up here, minus the guys that are adjacent to it, and generalization of this at higher points. Right, so just keep that in mind. Now here's a very brief reminder of what this kinematical association was that we talked about last year. Now we're in Mandelstam space, and we can talk about a set of variables that are just the sum of consecutive momenta, pi to pj minus 1 squared. These are these capital Xij's. And the associahedron, this kinematical associahedron, is cut out by demanding that all these variables are positive, and that this interesting 4-term sum of the things having to do with I plus 1, jj plus 1, and this is the same as negative pi dot pj, by the way, that these are just some fixed positive constants where these variables range everything from 1 up to n minus 1, but you leave out n. So this description is breaking the symmetry between all the points and making one point special. It makes n special. So keep that in mind. All right. So if we turn on genericCij's, we get the shape of the general association. But there's a natural question. What would happen if you start turning off theseCij's? Well, it'll get more and more, it'll shrink, right? So what happens if you go to the extreme and you turn all of them off? If you turn all of them off, it shrinks to nothing. Let's say you turn all of them off but one, C. Well, that's a simple question. It turns out that there is one of the C's that's special. All the other ones, if you turn all of them off but one, you collapse the space down to something that's not top dimensional, but one. And this one makes two other points special, 1 and n minus 1. Okay? So you have to set C1 n minus 1 to be non-zero, all the rest of them are 0, and what you get is a simplex. So this is what it is for n equals 5. So if you put C1 for non-zero and the rest of them 0, you get this little triangle, and you get instead these little intervals if you turn off all but the other guys. Now, it's now an obvious fact that the full isosahedron is a so-called Minkowski sum of all these different pieces. So this is a natural decomposition. It's not just that we have an isosahedron, but it comes with a particular decomposition into a preferred simplex plus a bunch of other little pieces. Okay? All right. So let me go back to this simplex. How do I describe it? I can just leave it like this if I like. It's just a triangle. The sum of all these x's adds up to the c, which I've left non-zero. But this is solved also by saying, because there's other variables for describing the simplex, that this x equals 2 is some constant multiplied by the difference between two ordered sigmas. In other words, this simplex looks exactly like a gauge-fixed worldsheet. Now in kinematic space. Okay? Now there are three things that are special. 1, n minus 1, and n. To begin with, only n was special, but more is special because 1 and n minus 1 are also singled out as giving you a simplex in the end of the day. All right, so let's go back to getting functions out of these canonical forms. So if I go back here and I do exactly the regulation that we talked about to get a function out of the canonical form of the isosahedron, then unsurprisingly that gives me the amplitude back. So that's another nice way of getting the amplitude, just by integrating this canonical form. Okay, so, and if you degenerate this guy, what do you get? Well, if you degenerate it in the natural way, seeing what happens if you turn off the c's one by one, if you degenerate it all the way to when you get a simplex, up here are the powers that appear, or the phase variables associated with the isosahedron. But after you degenerate, you have to change the powers in the way that I told you, by putting these extra factors in here. And now, purely in the statement about regulators, you discover an integral over the worldsheet of Park-Taylor factors with the cobinomial system. Okay? So, beginning from the standard picture of the kinematical space association, observing that there is this natural simplex sort of given to you from the Minkowski sum decomposition, and taking the limit, still just as a statement about regulators, you discover that the regulated form of the answer, to integrate the canonical form in kinematical space, looks like a string integral. There's no CFPs, there's no correlation functions, it just looks like a string integral. And of course, this is just Park-Taylor, we're not doing anything else yet, so this is really Z-theory amplitudes, if alpha prime was finite. Alright, so I think that's quite interesting. So just as a method to get the answer, it's natural to introduce a regulator. And if you do it on this degenerate object, and now you just declare that the regulator is finite, you get a string amplitude. Okay. From kinematic space. Now, you can ask, what's wrong? Why did I degenerate it? Why not just stick with this guy and just do the same thing, leave alpha prime finite? And here, there's something I think also quite interesting, is that, forget about physics, there's something internally wrong with this. There's some property that it could have had that it fails to have, which is the function. You see, as you said, alpha prime to 0, this canonical function has the property that when you go to the faces, it reduces to the canonical function on the faces. That mirrors the statement about canonical forms, that they reduce on the boundaries, the residues reduce to the forms on the lower faces. However, it's easy to see, for reasons I don't have time to explain, that in this case, that fails to be true at non-zero alpha prime. So there's something deficient about this, purely as a extension of this notion of a canonical function. In physics, this means that these quote-unquote amplitudes would fail to factorize, even on massless poles, for non-zero alpha prime. Okay, so they would not, so all the higher dimension contact operators you get, they would fail to give you an amplitude that correctly factorizes with all of them. Whereas, of course, the string one does. So, now, one way of seeing what the problem is here is that if you go to these boundaries, so things sort of diverge and localize, but these extra wall factors far away are not equal to 1 on that boundary. They still vary. They can't go to 0, but they're not equal to 1. and therefore they're not the same as what you get if you only lived on the boundary to begin with. So here's a natural question. Which polytopes, of all polytopes in the world, they all have canonical forms, but which ones have the property that we can consistently UV extend them, somehow alpha prime deform them to polytopes whose associated functions have this nice property that they go into themselves as you go down to the boundary. See, to be able to do that, somehow you need to be able to give a description of the polytope which is more extreme than the one I gave you. You need to be able to give a description where when you go to some face, all the faces that don't intersect go to 1. Okay, so they don't have any variance at all. You need a more binary description of this polytope. You can't do that by cutting it out with flat inequalities. But here's a simple question that you could ask. Are there polytopes that can be cut out, have a curvy binary description of the form that you associate variables capital F of all the faces that satisfy an equation of this form? The capital F is equal to 1 minus the product of all the faces that don't intersect this one of all the other guys. You see, if these nonlinear equations are consistent, if they cut out the space of the appropriate dimensionality, then they do exactly what we want. Because when this variable goes to 0, all the faces that don't intersect it are forced to go to 1. And so on. Okay? Now, that's just a beautiful combinatorial problem now. And we've been studying this for the past couple of weeks. And it appears that the answer, we haven't proven this yet, but in low dimensions we seem to have proven it. It appears that the answer is that this is not true of random polytopes, it's only true of associahedra. Products of associahedra. Associahedra are the answer to this natural question of polytopes that can be given a binary representation in this way. And I think this is really remarkable because it's the associahedra in turn that give us this factorization property on the boundary. But we're not asking for that factorization property on the boundary. It's an output of this sort of natural question of being able to describe polytopes in this extreme curvy binary way. And here, here we're assuming that all the powers here are 1 when making this statement. There's a natural conjecture that if we allow general powers, we'll discover more general things than associahedra, and perhaps we'll discover all the polytopes associated with all the cluster algebras, maybe more, but certainly already, even in 2 dimensions, we seem to have exhausted everything you can get with a square, a pentagon, a hexagon, and an octagon, and those are exactly the things that are associated with A1 cross A1, A2, B2, C2, and G2. Those cluster algebras. So, and we don't seem to be able to get anything else, even when we try general powers. So I think it would be fascinating if this was like, if this was a natural definition or reason why we should care about these cluster objects to begin with. But anyway, we'll see how that goes. Do I have negative time? I have 1 minute. Next time, yeah, next time. Yeah, that sucks, guys. Sorry. What can I? All right. Okay. La la la. Yeah, 5 minutes. Literally 5. Literally 5. Guys, I promise 5. Don't worry, public lecture people. I'm not going over time. I'll go less time. Anyway, there's general questions about the vacuum wave function, and even in flat space field theory or the cosmological wave function in general. There's a nice toy model, which is to just think about conformally coupled scalar fields in FRW cosmologies, or completely equivalently, a theory of a scalar field with ordinary kinetic term but time-dependent interactions. And you sum the usual Feynman diagrams we always sum, and we get, except with the difference that there are boundary conditions, when we do the Passano rule, that the field is fixed at some future time at equals 0. So that's what turns it into a cosmological calculation rather than calculation of amplitude. But already it's more interesting. These are things that we're not used to seeing when we think about amplitude, but for example, we have to expand the propagator really out of the usual Feynman propagator with 2 time ordering, so we have to work in time space. We don't have time translation invariance. There's a correction that takes into account the correction calculating the vacuum wave function. So already even one Feynman diagram can get complicated, because the propagator has 3 terms, and if you have, E internal edges, it has an order 3 to the E terms. But what it depends on in the end are these variables. There are these variables that I call x and y associated with the vertices and the edges, and they're just the energies. They're just, so it's not Lorentz invariant, they're just the energy variables associated with these guys. Okay, so that's the Feynman way of talking about these things. And there's also old-fashioned perturbation theory. And you can, the old-fashioned perturbation theory is a different expansion. The final answer is the same. It's a different expansion where, which you can derive in various nice recursive ways. I don't have time to talk about it. But just so you have an idea of what these things look like, you know, this would be, for example, a 3-point amplitude, and all these diagrams would truncate all the lines going out to the boundary. So 3-point coupling would just be 1 over x. This is a 4-point coupling, which is already a sum of 3 terms with the collapse of something simple. This is simply 1 loop at the level of the integrand. If there's 7 terms, but it collapses to something pretty simple. This 5-point thing, by connecting, making it look like an amplitude, the sum of 9 terms, it collapses to something simple. And so you can ask the same question as before. Is there a geometric object that calculates this, blah, 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 blah. Okay? And the answer is yes, there's a geometric object that calculates. But before going there, I want to tell you why as an amplitudologist you should care about these things. Because these objects contain scattering amplitudes. In fact, they regulate scattering amplitudes. They contain them in a nice way. And precisely because we don't have energy conservation, we have this finite time cutoff at 8 equals 0. But instead of having poles when the sum of the energies go to 0, instead of having a delta function, there's a pole as the sum of the energies go to 0. And the coefficient of the pole is the S matrix. So the residue on this one pole is the S matrix, simply because that pole arises from a limit where all these time intervals go up to minus infinity together. So for instance, if I go back to this example, at 4 points I had this guy, but if I sit on this pole where x1 equals minus x2, you see I have the product of 2 factors. The product of 2 factors turns into 1 over x1 squared minus y squared, and that exactly turns into a Lorentzian propagator. Okay, so it's the usual thing you're used to from old-fashioned perturbation theory, that the Lorentzian propagators come from factorizing to the product of 2 linear pieces in energy space. And that's in a sense what all the story is about, is that linearization, that breaking apart of the Lorentzian propagators into products of more pieces and more. Now, loop level, this is already interesting. If you take this guy, and you take this pole, you get something that looks like a Lorentzian pole, but it has 2 pieces, which is 1 over the energy associated with that loop, and 1 over the energy associated with that loop. Of course, this doesn't look like the product of Lorentzian propagators, but it shouldn't. It couldn't. Because in this problem, all you know about are spatial momenta. So there could never have been, at the level of an integrand, there could never have been something that has an L0 in it. And in fact, what this thing matches is exactly the Feynman tree theorem calculation, okay? Where you do the L0 integral using the epsilon. If you do the L0 integral using the epsilon, you get something that only depends on spatial momentum, and that's the expression you get. Okay, now, there's more things. I don't have time to tell you about these things. When you really do these calculations and consider full to the end, you actually get polylogarithms. Polylogarithms are more complicated, but anyway, of course, the answer is going to be that all these things are calculated in a simple way for the polynomial polytope, but let's never mind that. Let me at least define, just so that Kala doesn't kill me for the 7th time. Let me just define the cosmological polytope. There's a very simple definition. You begin life, imagine you have a collection of triangles with vertices A, B, C, and they only have the property that they are allowed to intersect other triangles on 2 of the 3 sides. This funny business with 2 of the 3 sides is really encoding the physics of the light code. As you see when you start studying this more and more, the sort of 3-ness with 2 things of one sort and 1 thing of another is really mirroring the fact that in the space-time you have the past, future, and space-law. But that's it. That's the entire definition. And then everything else after that is exposition. You can see that they're associated with graphs. I didn't say anything about graphs, but you just allow these triangles to intersect together, and you see that they're associated with a picture of graphs, where instead of gluing edges to vertices, you glue segments along their endpoints. Anyway, I won't tell anything about the detail, but let me at least just make this claim that one of the faces of, so the canonical form for this cosmological polytope calculates the wave function. Okay, that's the claim. Just like the amplitude and the association, exactly the same story. The canonical form of the cosmological polytope calculates how the wave function of the universe for that graph's contribution to the wave function of the universe. But there's a particular face of this guy where the sum of all the energy variables goes to 0, the one that should reveal the amplitude. And the cool thing is that at tree level, this thing is just a simplex, And it just generalizes what I showed you before. The product of the energies turns into the product of one of the Riemann systems. At loop level, it's not a simplex. It's more complicated than a simplex. You can triangulate it with vertices just of this polytope itself. And quite beautifully, all the triangulations of this guy correspond one-to-one with all the ways of doing the L0 integrals, which can get more and more complicated when you can close the contours upstairs, downstairs, decide which things to do in what order. But every way of doing the L0 integrals corresponds to one of the triangulations of this amplitude facet. So you can really think of this particular face of the cosmological polytope as a polytope associated with the prime entry. All right, so I'm done. Let me just say that I think certainly from when I was first saying these words in this room around 10 years ago, I certainly didn't imagine that there would be as much progress as there's been, and I really can't wait to see what we'll see in the next 10 years. Thanks a lot.
Any questions? Just two on there.
Okay, so when you define the amplitude of the integrand, introduce those regularization factors.
Yes.
I mean, you mentioned that mathematicians tell you what they put in. So how constrained are they? So
they're just variables. They're not constrained at all. They're constrained to be, I mean, to regulate, they're constrained to be positive.
Try to reproduce the string amplitude.
Yes.
But I mean, otherwise, anything.
No, it's not. You can't put. I mean, there's a reason why. There's a reason why people like Gelfand were introducing these things, never having heard about string amplitudes. Okay. So there, and what's special if you put random functions that damp things. The special thing about these guys is you get meromorphic functions of the variables that occur in of the regulating variables. It's not obvious to get meromorphic functions in general at all. But these simple powers give you meromorphic functions. I agree. We'd like to understand why we don't do many other things too, but it's not I mean, people who had never heard of string theory were doing this. Euler was doing this a long time ago. Euler didn't know anything about string.
In other words, I was trying to see if it's a way to actually calculate amplitudes from amplitude theater.
That part of the talk is not, at the moment, giving, I can't imagine how it would right now, but it's not giving you a new formula for the string amplitude. It's really something just slightly more conceptual to say that there's something you can do. I mean, you have these canonical forms in kinematical space. That's the mantra of this talk, is that we should stay in kinematical space. Think that's the space for the amplitude to live. Not in auxiliary places, no world cheats, no Grassmannian. Stay in physical kinematical space. And that there's a question that emerges in physical kinematical space that looks like the world sheet. That's sort of surprising. And that's something, a natural thing that you do leads you to Kobe-Nielsen factors, the Park-Taylor, the whole shebang. Whether it extends, I mean, what I told you is what we know. It might be coincidental, it might not mean anything. I doubt it, but...
Okay, given the late time, let's thank Nima again.